Hello dear students, welcome back. We are now in part 3 of our gravitation chapter. So let's just quickly revise what are the topics that we have done so far. So mainly what we have done is discussed the variations of acceleration due to gravity, that is small g. Okay, so why does small g change? So first of all, what is the basic formula for small g? It is g capital M by r square. Okay, so capital G is universal gravitational constant, M is the mass of earth, and r is the radius of earth here. Okay, and what does this value of g, usually we take it as 9.8, or in MCQs we can round it off to 10, okay, meters per second square. And where is this value of g to be considered? So it is on the surface of earth. Now how does this change, right? So what is the variation in it? So the first thing is, if we are at a height h, then all you can do is replace the denominator, which is capital R, with r plus h. Okay, so that is the height h measured from the surface of earth. All right, or if you want to express it in terms of small g, okay, that is the acceleration due to gravity on the surface, then you can write it as small g into r upon r plus h, the whole square. All right, then for LEO satellites, what do we mean by LEO satellites? Any satellite which has a height of less than 800 kilometers, very close to the surface of earth, okay, because satellites can be quite far away from that. Then the formula is gh is equal to g into brackets 1 minus 2h by r. Okay, so there is no square here. All right, and what about variation due to depth? Instead of h, now we have d. Okay, so that is acceleration due to gravity at the depth gd. G is equal to g into 1 minus d by r. Okay, and finally we also saw variation due to rotation of earth. Okay, so that is g dash. It is going to be g minus r omega square cos square phi. Okay, omega is the angular velocity of earth, phi is the latitude. Okay, more details we will discuss during the derivation of this formula. So these are all the formulae that we have discussed so far. Okay, please note none of the derivations we have done, which we will be covering up later on from the college exam point of view using the zip files which I have been sending you. Okay, so we had also solved numericals for this. This was in lecture number 2. Okay, so now we will continue. So today's lecture, okay, we are first going to begin with graphical representation of all of these values of small g. Okay, so when I say a graph, okay, so that means I need my y-axis. So on the y-axis, I'm going to plot small g. That is our acceleration due to gravity. And since it's going to change, okay, so that's why the value on the y-axis is going to change. And it is going to change with what? Okay, so on the x-axis, it is basically going to change with small r. So what is this small r? Small r here represents the distance from the center of the earth. So if I consider the origin here, see the origin, right, that means the small r is 0. So the origin on this graph basically means the center of earth. So starting from the center of earth, how does the acceleration due to gravity change? We want to know that. Okay, so what we can do now is, let's just consider the basic formula that we know. Okay, so that is gd is equal to g into brackets 1 minus d by r. So what we have here is a point. Okay, now how do we get the coordinates of this point? What are the coordinates, x and the y coordinates? So for that, what we will do is we will just substitute the value of small d equal to 0. So if I put the value of small d equal to 0, what it means is I'm at 0 depth. That means I'm on the surface of earth. So 1 minus 0, okay, 0 upon r is basically 0. So 1 minus 0 is going to give me 1. And into g, small g, right, is going to give me small g. So gd is equal to small g, and we know the value of small g. So what is my x and y axis values? Okay, so the x axis value is going to be capital R. Why? Because how far am I from the center of earth? The origin is the center of earth. So how far am I from the center of earth? If I put 0 depth, I'm at the distance capital R, right? And what about the y axis value? We know it's going to be 9.8. Now, if I start increasing the value of the depth, so in this equation here, if small d is now not 0, if it is increased further, then what is going to happen? Now, it's going to be 1 minus some number here. right? If I put small d 1 kilometers, 2 kilometers, 10, 15, 20, 100, 200, like that, if I increase the depth, if I go deeper and deeper into the surface of Earth, then what's going to happen is it's going to become 1 minus a bigger number. Slowly, 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 this number is going to become big. So 1 minus an increasing number is going to give me total, this whole bracket is going to reduce. And if this whole bracket is going to reduce, then what will happen to the value of GD? GD will now start going down. It will decrease. Okay. So at different depths, if I point, all these points here, if I plot them for different values of depth, then I'm noticing that it's going down. And if I join all those points, I'm going to get a graph which is going to be a straight line. So now the first question arises here is that why is it a straight line? Why can't it be a curve? Okay. So now this is some basic maths that you need to understand. You may or may not have covered it right now when you are studying this chapter, but definitely at some point of time in maths you will study whenever you have an equation like this where the y-axis value, okay, so this GD is what I'm trying to plot here. These are all the values of GD. So where the y-axis value is directly proportional to the x-axis value, the degree is 1. What do you mean by degree? Degree means the power of the x-axis here. So the x-axis is the distance, okay, which is being represented by this small d here. And the distance, small d, its degree is basically 1. It's d raised to 1. So since it is d raised to 1, the degree is 1, the graph has to be a straight line. So please note this. If y is proportional, directly proportional to x raised to 1, okay, if you have this kind of an equation, the graph has to be a straight line. So that is the reason why you are getting a straight line graph, and ultimately when you reach a depth equal to r, so if I put the d value equal to capital R, okay, so if the d value is capital R, then r upon r becomes 1, and 1 minus 1 will become 0. And that's why the y-axis value will turn out to be 0. So basically the graph starts from the origin. Okay, it starts from the origin and it rises up till 9.8. And now I have reached the surface of Earth. Alright, so now let's go to a height h. Okay, so this is within Earth. I'm still inside Earth. Now let's go outside Earth. So the moment we are raised from the surface of Earth, the first thing we could do here is use the formula GH is equal to G into brackets 1 minus 2H by R. And if you recall, this formula is for LEO satellites. That means satellites which are very close to the surface of Earth. Okay, so we can say, within 800 kilometers. So if I'm close to the surface of Earth, then again the graph is going to be a straight line, but this time again it's going to decrease. Okay, it's not going to go beyond 9.8. 9.8 is the maximum value. It's going to reduce. Why is it going to reduce? Well, the reason is, see the equation. So again I have 1 minus something. So if I have 1 minus a number, that means that number is less than 1. So if I multiply small g, which is 9.8, by less than 1, I'm going to get less than 9.8. So the graph has to go down. So one thing you are understanding here is the maximum value of small g is 9.8, is basically on the surface of Earth. Okay, so it's reducing, fine, but why is it also a straight line? Okay, so check the equation. The equation says it is going to be 1, right? Small g brackets 1 minus 2 h raised to 1. Again the degree is 1. Okay, the distance here, the degree for the distance is 1. Capital R is a constant. It is the small h which is a variable, and the degree is 1. So again it's going to be a straight line. But this is, as I said, only for very close to the surface of Earth. So if you are not close to the surface, so here this point on the x-axis is just little bit more than capital R. Okay, so r plus h, some small height h. Now what if we go further beyond this distance? Okay, so now let's go away from the center of the Earth and away from this close orbit or LEO satellites. Okay, so what is going to happen? We have to change our formula. So it's now going to be GH is equal to G into brackets R upon R plus H the whole square. So now you can clearly see the degree for H has now become 2. Okay, the degree, the whole denominator is squared. So it's H square. So and that too in the denominator, it's not in the numerator. So it is inversely proportional to the square of the distance. So if that happens, okay, so if it's going to be inverse, so if it's inverse basically means it's going to reduce, right? As the x-axis value increases, as the h value increases, the gh value will decrease. That's what inverse relationship means. And square means it's not going to be a straight line anymore. So this graph from this point where this green line ends, after this point, it's not going to continue in a straight line. It's going to become away from the radius, far away from the radius of Earth, from the surface of Earth. It's going to become a curve. Okay, and eventually it keeps on reducing, and at some far away distance, again, if you are quite very far away and out of the Earth's gravitational field, then it may even become zero. Okay, so it reduces, and at infinity, practically speaking, it will become zero. Okay, so this is a very important graph to understand all the variations of small g, especially with depth and height. Okay, so again, just to recap, beginning from the center of Earth, we are at the origin, no acceleration due to gravity. Then as we come closer and closer from within Earth, from inside Earth, if we come closer and closer to the surface of Earth, then the small g value is going to increase. It will reach a maximum value of 9.8. Initially for some distance, again it will decrease with height, and then it's going to become a curve. Okay, initially it will be linear and then a curve. Okay, so this is the graphical representation for variation of acceleration due to gravity, especially with respect to depth and height. Okay, all right, so now we begin with the next topic in the chapter, and that is how to launch a satellite. What is the process of launching a satellite? Okay, we want this satellite to go around Earth in an orbit. So how to do that? So let's understand this basic concept of throwing an object up in sky. Okay, so you see these kids here, they are playing with this ball, and they're just kicking the ball up. So every time they kick it up, right, every time the ball is kicked up, it goes up. But then what happens to the ball? It falls down again. Okay, so what is it to be learned from here? Whatever goes up must come down. So then obviously, if I am launching the satellite, is it going to come crashing down? Or is it that it's right now very far away from Earth, right, several hundred kilometers and maybe several thousand kilometers? So yes, slowly it is coming down, and one fine day it's going to fall on our heads. Okay, so let's understand, how does a satellite revolve in an orbit? Okay, it's not going to crash onto our heads. So how do we take care of this situation? How do we make sure that the satellite just keeps on circling around Earth and it doesn't fall back? Because if I just put it on the rocket and release it and just throw it up in space, and not do anything else, then it's going to fall down. Okay, so if I don't want that to happen, what is to be done? Okay, so the answer is we need a multi-stage rocket which eventually sets itself into the orbit. Okay, eventually it enters into the orbit. Okay, so how does this happen? Okay, watch this clip carefully, it will make you understand. So just see what's happening here, and then we will see in detail, okay, how the satellite achieves its orbit.
Liftoff of the Delta rocket carrying GLAST, a gamma-ray telescope searching for unseen physics in the stars of the galaxies.
Okay, so I'm just playing the clip again in fast forward, and you can see carefully, if you notice, okay, what was happening to the satellite. It is changing its orientation. It's not going vertical. Okay, so see again, you see it's changing the angle. Okay, and then right now, if in this part you can see it's almost going to become horizontal. So that's the idea, right? The satellite has to become horizontal and launch itself into the orbit. Okay? It has to catch that particular orbit, or it has to come up to the right speed horizontally. Okay, and then what happens once it leaves Earth's atmosphere? Okay, so watch this clip now. So what we can understand is there are multiple stages to every satellite. Okay, eventually, slowly, as it rises up in sky, initially it may seem to be going up vertically, right? It will tilt slowly. The different stages will keep falling off to reduce the weight, and then ultimately the satellite will catch its orbit. Okay, it will just join that orbit. So now a very important question that arises here is, what is the speed? Can the satellite just go at any speed, okay, if it just wants to start revolving around Earth, okay, in a circular or an elliptical orbit? What should be its speed? Okay. So that speed is called as the critical speed. So whenever this word critical is used in physics, at least 3 places in physics in the entire subject, you will see this word critical speed is used. Okay, critical speed in this chapter basically means, okay, it is that speed which is needed to achieve a circular orbit. And why this word critical? Like, for example, if there is a patient in a hospital, okay, so the patient in the hospital, if we say the patient is critical, okay, what does that mean? It's like a boundary stage. Okay, so anything, if the person crosses this boundary, anything can happen. So the same thing with our satellite here. Okay, it has to get this critical speed, because if it crosses this critical speed, then it may get something called as the escape speed. So what do we mean by escape speed? So watch this clip now. So you see this is from a movie, and you see this person, this astronaut, was thrown with some speed, and if the speed is high enough, you could see that person is just escaping far away from Earth. Basically, the person will just go at such a distance, like Earth will no longer have any influence on that person or that object or that satellite, whatever it is. Okay, so this person here was thrown out with probably the escape speed, and if he or she does nothing about it, then he will never be able to come back to reach Earth. So what are the different possibilities for different velocities? Okay, so let's understand that, because based on the different velocities, the trajectory of the satellite will change. What do we mean by trajectory? What does this word trajectory mean? Trajectory means that path which the satellite achieves. Okay, it may be circular orbit, it may be elliptical. Okay, so what are the different possibilities? Let's talk about it. So here we have our Earth. Okay, and there should be stars around, but just neglecting all the stars, we're just looking at Earth. And at some point here above the Earth, okay, at a particular height edge, I'm going to launch my satellite, where my satellite has to be at this height. Okay, so now what are the different possibilities? Okay, so the first possibility is that I can launch the satellite with a speed which is less than the critical speed. So that's why this word critical. Okay, if it is less than critical, then see what happens. I've said written crash, right? So most probably what is going to happen is it will achieve an elliptical path. So this is the first case. It will achieve an elliptical path, but the trajectory of this ellipse will enter into Earth's atmosphere. And once it enters the Earth's atmosphere, because of friction, air resistance, the energy of the satellite will keep on reducing and ultimately it will crash on Earth. It will not be able to go, it won't be able to complete this circle, right? It will just crash onto the surface of Earth, right? So the entire ellipse will not be possible at all. So that's why this word critical is used. You see, if the speed is less than the critical, we lose the satellite, which may be costing, billions of dollars actually. All right, so we don't want this to happen. So what should we do? We should launch the satellite in the second case, which says that the speed with which, the speed at which it enters the orbit, it should be equal to this critical speed. Okay, it should be exactly equal to this critical speed. And if that happens, my satellite is going to achieve a circular orbit. Okay, it's going to be a nice circle around Earth. And this is what we would usually prefer. Okay, what if the speed becomes more than the critical speed, but still less than that escape speed which we saw in the previous slide? Okay, so the satellite is not going to escape. It's a little bit more than the critical speed, but not so much more that it escapes out. So again, I will have an elliptical path this time. Okay, but this ellipse, the shape is such that the trajectory never enters the Earth's atmosphere. So since it never enters the Earth's atmosphere, okay, it doesn't crash into Earth. It can complete the entire trajectory. So if it starts from here, it can go around and come back. Okay, it can complete the entire trajectory without crashing into Earth. Okay, and sometimes we may want satellites to be in this kind of orbit also. Okay, elliptical orbits are fine. Okay, but what if the speed becomes so high? Okay, that speed with which the rocket is firing, if that speed becomes equal to the escape speed, so it's very obvious, if the speed becomes equal to the escape speed, the satellite is going to escape. That's why this word escape is used, right? It's going to go away. So what kind of shape is the trajectory going to have? It's going to have what is called as a parabolic shape. Parabola is one of the types of a curve that you are going to study in mathematics. Okay, ellipse, circle, ellipse, parabola, hyperbola, these are different curves that you are going to study, okay, in conics, in the section of conics in maths. So you can see clearly here this parabola. Okay, I have put arrows. Okay, it's not a closed curve. Ellipse is a closed curve, circle is a closed curve, parabola is not. That means if the satellite is in the parabolic trajectory, okay, it's just going to go away either this side or this side based on whether I throw it to the left or the right. So if it is thrown on this side, okay, it's just going to go on this path and that's it, it's gone. It will never come back to Earth. So as it's going, okay, as it is going like this, okay, you may still see from Earth, you may see, oh, the satellite is right there, and you may feel, oh, okay, fine, the satellite is there and it's still in our control. But please note, no, eventually you will lose the satellite, okay, if nothing is done. So that's why this word critical is used. It's very important because it's a very costly thing that we are dealing with here. So the speed has to be just right. Okay, so it will escape out in a parabolic path. And what to speak of if the speed is more than the escape speed, then obviously it's going to escape out, but this time the trajectory is going to be what we call as a hyperbola or a hyperbolic path, which is even more extended, stretched than a parabola. Okay, and basically if it goes along the hyperbola again, it's not a closed curve, it's an open curve, so the satellite is basically lost if nothing is done. Okay, so these are the different cases, okay, for launching of the satellite in different possible trajectories. Okay, so what we would prefer to be is in case number 2 and 3. Okay, either a circular orbit or an elliptical orbit where the speed is less than the escape velocity. Okay, we want it to be either equal to the critical or more than the critical but less than escape. This is what we would prefer. Anything beyond that, we lose the satellite. In the first case, it just comes crashing to Earth. In the fourth and the fifth case, we lose it. It just goes into free space. It may go and crash into some other planet Okay, and if nobody else, then maybe the sun. Okay. So now, if the critical and escape speeds are so important to be known for a satellite, because the astronauts, the scientists who are launching these satellites, okay, they need to know how much fuel to burn, what is the power of the engine, how many kgs of fuel per second is being burned, what is the force which the satellite is achieving, and based on that, it will get that critical speed. So for that, we need to know what is the desired speed. Okay, so we need to know what is the formula for the critical and the escape speed. Okay, so again, we will just take the formula for granted. All derivations will be done together using the zip files which I've been giving you. Okay, so the formula for the critical speed here, okay, is square root of gm by small r. Okay, so capital G is the universal gravitational constant, m is the mass of the earth, and small r is the distance from the center of earth. So you can replace small r with capital R plus h plus, but just please note here, this speed, critical speed, is in the orbit. Okay, critical speed obviously means we want a circular orbit. Okay, if you are in this orbit, then this should be the speed. And what about the escape speed? So the escape speed is going to be, the formula is square root of 2 times. Okay, so the number 2 is there in the numerator. Again, capital G, capital M in the numerator. So same as escape critical speed. But the denominator here is different. It is capital R. It is the radius of Earth. What does this mean? This means that this escape speed is not just anywhere. It's not for a satellite in orbit. Okay. In fact, it is on the surface of Earth. It is for a body on the surface of Earth at rest. So if there is some object at rest on the surface of Earth, and if I pick it up and I throw it and I want it to escape the gravitational influence of Earth, it should go into some other planet, should escape out Earth. Okay, then this is the speed with which it should be thrown. So if you plug in the numbers, because all are constants, 2, capital G, capital M and capital R, everything is a constant here. If you put in the numbers and calculate, you are going to find out it's going to be 11.2 kilometers. Okay, kilometers in 1 second per second. Okay, that's very fast. Okay, so fortunately we don't have any machine which can do that. Okay, or maybe unfortunately, because if there was a machine which could throw an object with this speed, then it would become very easy to launch things out of Earth's influence, so that they can reach probably Mars or Jupiter or Pluto or wherever we want to send these different probes. We send, right, everywhere in our solar system. So we can just throw it with this speed, but unfortunately such a thing doesn't exist. And fortunately good enough for us, because if somebody throws us with that speed, we are gone. Okay? So 11.2 kilometers per second, it's a very high velocity. Okay? Eventually it can be achieved though. Okay? That means when the satellite is in orbit, okay, or it is out of the Earth's atmosphere, and if it is thrown with several kilometers per second, which is possible, okay, then it is still that may happen, that the object is lost, okay, into space. Okay, so please note down this formula. Important, you have to memorize them. Okay, VC root of gm by small r, VE root of 2 gm by capital R. Okay, all right, so let's just solve one numerical today related to this concept. So we are now doing GTB. GTB stands for government textbook. Okay, so the textbook that I had shown you in the previous lecture, okay, and also in current electricity. So use that textbook. Question number 4 in that textbook, the second one within it. Yes, question 4 are all numericals. So the second numerical in question 4. So the question is, if the Earth were made up of wood, okay, right now it's not, but suppose if it was made up of wood, the mass of the wooden Earth would have been less. So how much less? It would have been 10% as much as it is right now. So if it is 10% as much as it is right now without changing the diameter, calculate the escape speed. Alright. So what can I say about the mass value? So the mass value, now let's say, I can understand now it's going to be a ratio question, because I'm going to compare the two speeds, right? So M2 is 10% of M1. 10% of M1. What do you mean by 10%? It means 10 out of 100. So 10 divided by 100. So what is 10 divided by 100? It's going to be 0.1, right? 0, 0 gets cut. So I get 1 by 10. 1 by 10 is 0.1. So M2 is 0.1 M1. And since I have understood it that it's going to be a ratio question, I can just say M2 by M1 is 0.1. So if M2 by M1 is 0.1, okay, what is our formula which we need for escape speed? Okay, so the escape velocity is square root of 2 gm by capital R. And since I know it's a ratio question, what I'm going to do is replace the equal to sign with a proportional sign and remove all those things which are constants. Okay, this concept was covered in current electricity, okay, when I discussed for the first time, okay, how to solve ratio questions. So replace the equal to sign with proportional sign and remove all those things which are constant. So 2 is a constant, capital G is a constant, capital R is not changing. You see they are mentioning in the question without change in the diameter. So the diameter or the radius of Earth is not changing. But what about the mass of Earth? Yes, that is changing. Okay, so capital M is not a constant here. So mass of the Earth is changing. All right. So if escape velocity is proportional, directly proportional to the root of the mass of the Earth, then I can just take a ratio now and say V2 by V1 is square root of M2 by M1. Right? Again, the sequence will remain the same. 2 by 1 here in the LHS and 2 by 1 in the RHS again. Why? Because it's directly proportional. If it was inverse, then I would have made V2 by V1 is root of M1 by M2. Okay, but since it is directly proportional, we will keep the sequence same, right? 2 by 1, 2 by 1. And we know this M2 by M1 is basically 0.1. So put that number 0.1. So please pause the video here and use your logbooks. Okay, do the log, anti-log and find out the square root of 0.1, okay, which may be challenging for you. So what you could do it is adjust the power of 10 so that the numerator is more than the denominator and all numbers are more than 1, because right now 0.1 is less than 1. Okay, so do the log calculation. You can pause the video, take a few minutes, find it out, okay, and if you do the calculation, you should get this number. V2 by V1 turns out to be 0.3162. Okay, so now V2 by V1 is this. Let's take V1, which is in the denominator, into the numerator. So I'm going to get 0.3162 multiplied by V1. And do we know what is the value of V1? What is the value of the escape speed right now on Earth? Okay, yes, we know it's 11.2. Okay, so 0.3162 multiplied by 11.2 kilometers per second. So if I do the simple multiplication, again, you can use your logbook. Okay, pause the video, do the log calculation again, and you are going to get 3.54. And since the unit for 11.2 was kilometers per second, it remains the same. Okay, 3.54 kilometers per second. Okay, so that's all for today. See you in the next lecture.